So today we're going to be starting something a little bit new. It's called absolute value functions. You're going to find that there's a lot of similarities between what we do today and what we did in last class, but ultimately this is something new. Last class we talked about absolute value equations, of course, which was only where you had one or two solutions. With absolute value functions, however, there's a whole bunch of solutions. In other words, we're going to be graphing this to see what it actually looks like. So today's plan, again, review solving absolute value equations from last class, introduce absolute value functions, and then we're also going to talk about graphing absolute value functions today. Okay, so the first question we're going to do is an absolute value equation, just like what we did yesterday. Let me remind you that when we solve absolute value equations, we need to be getting the absolute value piece, that would be this piece right here, all by itself first. So the first thing we're going to do is divide both sides by 2. Now, when we divide this right side by 2, we have to divide both pieces by 2. So I'll divide this one and this one by 2. This is going to leave us with the absolute value of 2x minus 6 is equal to x plus 4. Now, you might remember absolute value equations are a little bit weird because the stuff inside the absolute value can be equal to a positive piece, or it could be equal to a negative piece, because either way, it's going to be spitting out a positive relative answer, right? So what we do is we actually break this down into what I call a piecewise function. This is going to become 2x minus 6, or sorry, the absolute value of 2x minus 6 equals these two different pieces. It will be equal to x plus 4 under certain circumstances, but it might also equal negative x plus 4, which of course is negative x minus 4. So we have to solve both of these equations, where it's equal to this piece as well as where it's equal to this piece, on separate occurrences. So we can consider the first case, where 2x minus 6, would be the absolute value of that, equals x plus 4. And then we'll also consider the second case, where we have 2x minus 6 is actually equal to negative x minus 4. Well, under this first case, I'll start off. We can gather all of our x's together on the one side. So if I minus x from the right side, this is going to give us 1x minus 6 equals 4. And then I can add 6 on both sides. So I'll get x equals positive 10. In this case 2, we can do the exact same thing, except I'm going to have to add x on both sides. So this is going to give me 3x minus 6 equals negative 4. Then I'm going to add 6 on both sides. That's going to give me 3x equals positive 2. And then I'll divide by 3. So that's going to give me x equals 2/3. Now, just for good measure, it's always a good idea to check these answers you get as well. I'll just do the check in a different color here, just so it can stick out a little bit better. So for a check, which I'll do right over here, we can check x equals 10 by plugging it into both sides of the original equation. So we're going to go 2 times the absolute value of 2 times 10 minus 6, and we want to see if that's equal to 2 times 10 plus 8. Well, when we do the absolute value piece, because it's technically considered brackets, we should do it first. 2 times 10 is 20. 20 minus 6 is 14. So we're going to get 2 times the absolute value of 14, which is 2 times 14, of course. On the right-hand side of the equation, 2 times 10 is 20, plus 8 is going to be 28. 2 times 14, of course, is 28. So 28 equals 28. That confirms that x equals 10 is a possible answer. Now, we'll also check the other one. I'm just going to split this away so I have a little bit of room and I don't clutter it with the other one. We'll check the x equals 2 over 3 as well. So 2 times the absolute value of 2 times 2/3 minus 6. We want to see if that's equal to 2 times 2/3 plus 8. Now, this is going to cause us some troubles, of course, because we have fractions going on here. On the left-hand side, we have 2 times 2/3, which is 4/3, but then minus 6. Personally, I like keeping things all as fractions. For the purpose of this, you can turn it to decimals if you want to. It might be easier to throw it in a calculator that way. I will just use fractions on this one, but again, you can use either method, whatever you're more comfortable with. This is going to ultimately require us to say that it's 2 times the absolute value of 4/3, And instead of minus 6, I'm going to turn that into something over 3. That would be minus 18 over 3. On the right-hand side of the equation, we just have 2 times 2/3, which is 4/3, but we're adding 8 to it. And like what we did with this minus 6 on the left side of the equation, we should turn that into something over 3 as well. So 8 is going to actually be 24 over 3. What this is going to lead us to is if we clean up the absolute value bars over here, 4 minus 18 is negative 14. So really we're going to have 2 times positive 14 over 3. And we want to see if that's equal to 4 over 3 plus 24 over 3, which is 28 over 3. Well, 2 times 14 over 3, remember this is like 2 over 1 times 14 over 3. That's going to become 28 over 3 equals 28 over 3. So yes, both sides of those equations were equal to each other, so we can confirm that x equals 2/3 was another one of our solutions. So just a heads up, for more advanced absolute value equations, you can actually solve them using your graphing calculator. And this really becomes ideal when a question especially has more than one absolute value piece in it. What I want you to note is that you can actually put an absolute value function in your calculator by pressing the math button, then pressing the right arrow, and then selecting where it says 1 ABS. Now, on a TI-83, which is the older calculator, it only does the ABS when you plug it into your calculator. However, on the newer calculators, it actually ends up drawing your absolute value bars, and then your like little cursor shows up here and allows you to type and then close out your absolute value bars when you're all done. That's quite convenient, right? So if you have a TI-84 or something newer than that, you're actually going to find that the absolute value function in your calculator is a lot easier to use. If you have a TI-83, again, it's going to show up just saying ABS and then bracket. Anything you put inside these brackets is going to be considered part of an absolute value, right? So how we can solve absolute value equations, where you have an absolute value equal to something else, is you can actually graph both sides of the equation, of course, into your graphing calculator. So put it into y1 and put the other part into y2. Now the points of intersection of the two graphs is your solution to your absolute value equation. So make sure that when you plug in the left side into y1 and the right side into y2, when you check your actual graph and find the points of intersection, those points are your solutions. We're going to do an example right away. All right, so here's going to be an example where we're really going to want to use our graphing calculator to solve this absolute value equation. Because we have more than one absolute value in here, it's going to become a lot easier to solve this using a graphing calculator than it would be on pen and paper. So what I need you to do, and I do want you to follow along as we go through this, so pause the video as needed, if need be, is I want you to plug this whole chunk into y1 in your graphing calculator. Now remember, to get an absolute value piece, so to plug something like this in, you have to press math, then press the right arrow, and then select where it says 1 ABS. Okay, so plug this whole piece into y1 and plug this 33 into y2. Now, this left piece, the y1, is going to have a very strange shape to its graph, right? It'll be a little hard for us to predict at the moment, but I can tell you right now the shape is going to be pretty bizarre. y2, on the other hand, is just 33. That means the entire function of y2 is just going to be y equals 33. So in other words, a horizontal line up at the value of y equals 33, right? So when we set our window on our graphing calculator, we're definitely going to want our y max to be something bigger than 33. Just for good measure, you might want to make it 40. That way you at least have some room to work with. So what I want you to do again, if you haven't already, plug this entire equation or this entire part of the equation into y1 and 33 into y2, and then press your graph button. Now with the window I set, again I have my y min is actually way down at -10, but my y max I set up at 40. My graph, just as a rough sketch for you, if this is my window, we'll say, this is the screen of my graphing calculator, My window actually shows that my y-axis, so where x equals 0 is right in the middle, and my x-axis is down here. And then my graphs, and I'll just do it in a different color so they stick out. My graph of my y1 looks something like this, more or less. And the graph of my y2, which was just 33, looks something like this. So the solutions to this absolute value equation are going to be, and I'll change colors one more time, they're going to be these 2 points right here. Now, it's been a while since we've actually used our graphing calculator to find points of intersection, but in case you've forgotten, you can do this by pressing second and then trace. And when you do that, there's a bunch of different options that come up, but down at 5, it actually says you can find the intersect point. So you can find where these two graphs are actually going to meet. So I'd select that. Then you just use your arrow keys to move the little cursor which follows along your graph as close as possible to the intersection point. Once you do that, you can just press enter 3 times. So enter, enter, enter. And for the one on this left part right here, I actually got that the intersection point for x is x equals, to the nearest hundredth, negative 4.29. Then for the right piece, I'll do it again, second trace 5, and then move my cursor over. Just takes a little while, hold on. Keep on pressing the arrow key until it gets over, taking its time. All right, here we go. It is going to be 5.14. So this is x equals 5.14. I know it's been a long time since we've done this. We learned about this, of course, back in the quadratics unit. Quadratics has kind of come back a little bit here in some ways, or at least the graphing portion of this. Just remember, of course, to solve an absolute value equation, that's where you have absolute values involved, but there's an equal sign, so it's equal to something else. You can just graph the left-hand side of the equation, and then graph the right-hand side of the equation in y2, and find the intersection points. Most of the time, the hardest part about this is figuring out what your window is going to have to be. But because we knew our second point, or our second part of this, y2, is just y equals 33, we knew that we had to set our window so that we could actually see that. So for actual new information today, we're going to learn about absolute value functions. Let me remind you that a function is just a machine where you can plug in an x and it spits out a y. What we're dealing with absolute value functions is where y equals the absolute value of an entire other function. So with an absolute value function, I want you to note that no matter what x you plug in, your y value that gets spit out is always going to be positive. This is because we're taking the absolute value of the entire function. So no matter what got spit out by that original function inside the absolute value bars, that number is going to be guaranteed to come out as positive. Because if it was already positive, it'll remain positive. But if it was negative, the absolute value bars will switch it to be positive. Also remember that if y is positive, then that means on your graph, you must be up in the upper 2 quadrants, right? Y is positive up here, y is negative down here. So when you have an absolute value function, unless there's something on the outside of the absolute value function, you're always going to be up in quadrant 1 or quadrant 2. So we're going to start with a relatively simple one first. I want to remind you what the graph of y equals 2x plus 4 would be. Y equals 2x plus 4, of course, is a linear equation. X has just got an exponent of 1, so there's not going to be any curve to this. And the graph of y equals 2x plus 4 is shown below. Now, what we're going to do to make a graph of y equals the absolute value of 2x plus 4 is we're going to start by making a table, because this is going to kind of show us exactly what's happening with each of our points. So if I make a table, we'll say we'll have an x that we plug in, and we're going to see the y that gets spat out. Okay? What I usually do when I look at this, I just throw in whatever x's I'm confident about. Maybe we'll start with x is 0. We'll kind of make that this part of our chart. So if x is 0, then you throw it into 2x plus 4. 2 times 0 plus 4 is just going to be 4. Which shouldn't be a big surprise, because if you look at your graph, when x is 0, y was 4, right? Now, if we plugged in, let's say, x is 2, then 2 times 2 is 4. 4 plus 4 is 8, so we'd have a y value of 8. And that also isn't a surprise because if you look at the original graph, 2 has a y value of 8. Now, if we go the other way, however, something interesting happens. If we start by saying we'll plug in x is negative 2, well, 2 times negative 2 is negative 4. Negative 4 plus 4 is 0. And we've actually found our x-intercept, right? Which would be right here. Now, what really gets interesting is if we plug in a number below that. Remember on that last slide I said when you take the absolute value of a function, your answer should only be in the top 2 quadrants. This is still going to happen. Watch what happens when we plug in x is, let's say, negative 4. When x is negative 4, you plug it into the absolute value function up here. 2 times negative 4 is negative 8. Negative 8 plus 4 is negative 4. So really you're looking at the absolute value of negative 4, which is positive 4. Now going back to the graph over here, again, if x is negative 4, we're going to say y is actually positive 4. On the original graph, it was actually way down here at negative 4, but on the absolute value graph, it's been flipped up to the upper 2 quadrants, right? We can try one more for good measure. I'm kind of like losing space on my chart here, but if we plug in x is negative 6, 2 times negative 6 is negative 12. Negative 12 plus 4 is negative 8. The absolute value of negative 8 is positive 8, right? So again, at x is negative 6, y would be positive 8, whereas originally it was way down here at negative 8. Bottom line is, when you take the absolute value of an entire graph, the stuff that's below y equals 0 just gets flipped to above. So if we're going to draw the graph of this part of the graph that was already above the line is going to stay the same, but the part that was below the line of y equals 0 is actually going to be flipped upwards. So it'll look something like this. Now, something else that I'm going to expect from you in this unit is the ability to make something called a piecewise function. Now, a piecewise function was like what I showed you before, where you basically just take your absolute value piece and you set it equal to a big squiggly line where there's something here and something here. But actually generating this is a pretty useful skill for us because it really dictates what part of our graphs is staying the same and what part of our graph is actually getting flipped. Now, to express it as a piecewise function, you need to find your x-intercept. That's going to be the basis of your piecewise function. Now, usually to find an x-intercept, you set y equal to 0, and then you solve for x. But given that we actually have our graph here, it's pretty crystal clear that our x-intercept is x equals negative 2. So we can just use that as our basis right away. Now let me show you what I mean. When x is negative 2, anything where x was bigger than that is going to stay the same because this entire chunk of our original graph doesn't move. So in other words, when x is greater than or equal to negative 2, your graph of your absolute value function stays the same as the original. So to write this as a piecewise function, we can say the absolute value of 2x plus 4 is going to equal this giant piecewise function here, where it's just going to equal the stuff that was already inside the absolute value. Nothing changes. 2x plus 4 when x is greater than or equal to negative 2, because that part of the graph is staying the same. It was already above the x-axis, so it's not going to be moving anywhere. However, this part down below needs to be vertically flipped upwards so that it is above the x-axis. In order to do that, just like what we did earlier with one of those first examples, is we actually just multiply the entire original function inside the absolute value piece by negative 1. So we could say negative, in brackets, 2x plus 4, when x is strictly less than negative 2. Alternatively, you could break this piece down to negative 2x minus 4. I'm honestly not picky. I'll accept it one way or another. But just understand that to create a piecewise function, you need to be able to find your x-intercept and use that as the basis, which is this part right here, of that piecewise function. Look for the part that is staying the same, and look for the part that is getting flipped. So with that last example, that's how we actually graph an absolute value function when it's linear. But we can also graph quadratic absolute value functions as well. I want to remind you that when you have a quadratic in its just normal standard form, y equals ax squared plus bx plus c, you can find the x coordinate of the vertex, which is like the bottom or the top, depending on the orientation of your quadratic, by using this little formula, x equals negative b over 2a. Now, once you have the vertex, the easiest way that we had to graph these was using something called the 149 rule. That's where when you go over from the vertex to the right one, you go up 1 times a and graph that point. Then you start back at the vertex, go right 2 points, and then go up 4 times a and plot that point. Then you go back to your vertex and you go over 3 points from it, and then up 9 times a. Once you did that on both sides, instead of just right, you would go left on the next time, you would just connect the dots and you'd have a nice even curve. That was the easiest way we had for graphing quadratics. This is going to work the exact same with absolute value functions. Just make sure that any part that lies below the x-axis needs to be reflected above the x-axis. Also, just like with linear equations, your x-intercepts are super important because they're going to serve as the basis for what gets flipped and what stays the same. So we're going to start with this question. We'll do this one together and we'll take it one step at a time. If we wanted to graph the absolute value of negative x squared plus 2x plus 8, we would have a lot of work that we would have to do first. Personally, I start by finding the vertex. Now, we want the whole coordinate. We don't want just the x value, we want the y value as well. And remember, this should be the y value just of the original quadratic inside of here. Keep in mind, if we have a negative y value for our vertex, in the absolute value version, it's going to be flipped above the x-axis to become a positive y value. So we'll worry about that later. This will just make it a lot easier for us to graph our quadratic. So to find the vertex, we start by saying that x is going to be negative b divided by 2a. And in this question, of course, negative b is going to be negative 2, because the middle number is your b value, divided by 2 times a, and notice a is negative 1. Well, this tells us negative 2 divided by 2 times negative 1 is negative 2 divided by negative 2, which is just going to be positive 1. So x in this case is going to be 1. Let's use that to find the y value. And again, I will reiterate, we're just using this with the original quadratic inside because we are going to flip any negative portion of our graph once it's all said and done. So ignoring our absolute value bars, we could say y equals negative 1 squared plus 2 times 1 plus 8. This is going to become negative 1 squared, which is just negative 1, plus 2 plus 8, which gives us 9. Therefore, our coordinate of our vertex is the point 1, 9. And this is going to serve as a very useful coordinate for helping us actually graph the whole thing. I'd also like to point out the coordinate 1, 9, if you were to plot it on a grid, would be somewhere over here. That means the vertex in this question is actually part of a quadratic that isn't going to change. It's already in the upper two quadrants. It's not going to be moving anywhere. So the next thing I do with these questions is find the x-intercepts. I want you to recall that to find the x-intercepts, you set your original piece equal to 0, and then you solve for the value of x, because again, an x-intercept is where y equals 0. Now, we can either use factoring, or we can use the quadratic formula if we really wanted to. Personally, I'm going to use factoring on this one. So I'm going to say negative x squared plus 2x plus 8 equals 0. Now, with a negative in front of our x squared, usually we would have to use what I call the adapted sum product rule. That's where we look for a sum of 2 and a product of 8 times negative 1. And then we have to use that factoring by grouping thing where we split apart the middle term and it's a lot more work. Good news is, I think there'd be an easier way of doing this. For all intents and purposes, to solve for our x-intercepts here, we can just move all of the left-hand side stuff over to the right side here by just adding or subtracting it over. I can add x squared to both sides to get, well, x squared over to the right side, of course. And then I can minus 2x and I can minus 8. So this will give me 0 on the left side equals positive x squared minus 2x minus 8. The reason I shuffled all this over to the right-hand side is now we only have a positive 1 in front of our x squared, which means we can use the easier factoring method, which is just what I've always called the sum product rule. We're looking for two numbers with a sum of -2 and a product of -8. And if you think on that for a few seconds, you'll find it's actually going to be -4 and +2. Those are going to be our two numbers. Since we only have a 1 in front of our x squared, we can jump straight to factored form. This is going to give me 0 equals x minus 4 times x plus 2. So therefore, our x-intercepts are going to be what satisfies this equation. This is only going to be equal to 0 if x equals +4 or if x equals -2. And those points right there are going to be our x-intercepts. Now remember, the x-intercepts are important because they serve as the basis for how we're flipping our absolute value function, right? Those are going to be our pivot points. The graph is going to swing about those points. You'll see what I mean on the next slide. So now that we have the coordinate of the vertex as well as where our x-intercepts are, we can actually now sketch the graph. Before I even begin, I'm going to state my vertex, which I'll remind you was 1, 9. And we also have our x-intercepts, which we found to be x equals 4 and x equals -2. I'm going to plot all those points on my graph first before I even begin. So first of all, my vertex being 1, 9 is going to be this coordinate right here. And my x-intercepts being -2 and +4 are going to lie right there. Now I'll say it again. Remember that your absolute value function, because this entire function is surrounded by an absolute value bar, there is going to be nothing at all down in these bottom two quadrants. Anything that usually would be found down there is going to be flipped up to the top two quadrants. So I'll also remind you, because the stuff inside the absolute value bar is a quadratic, we can use our 149 rule to actually graph this. So the 149 rule says, start with your vertex. So I'm going to start up here at the top of the vertex, go right 1, and then up 1 times a. Well, a in this question is -1. A, of course, is the number in front of your x squared, so it's -1 in this case. So if I go at my vertex, right 1, and then up -1 times 1, that's going to put me right down 1. So I'll put a point there. Then go back to your vertex, go over 2 places, and then go up 4 times a. Well, 4 times -1 is -4, so we're going to go down 1, 2, 3, 4 points. Now, the next thing we have, of course, would be the 9 part of the 149 rule that says go back to your vertex, go over 3 points, and then up 9 times a. Well, 9 times -1 is -9. That just takes us down to our vertex, which is already plotted. Now, to get this actually proper, what we should do is we should make it a symmetrical graph. So I'll plot this point over here, and I'll plot this point over here. So I've made this now a symmetrical graph. If you want, you can actually go one step further than the 149 rule. You might notice the 149 rule actually just it just deals with perfect squares. The next part of a 149 rule would theoretically be 16. So if you wanted to, you could actually plot a fourth point off of this on both sides using 16 times a. Well, 16 times a is -16, and if you go from 9 down 16, well, that's actually going to take you way down to -7. So I could actually plot a -7 down here on both sides. But then, of course, I recall I'm not allowed to have anything down in these two quadrants, so I'd be flipping that upwards to +7 over here as my actual coordinate. Just to reiterate what I did there, just in case you're confused, I plotted my quadratic as I normally would, but then anything that is below the x-axis needs to be flipped above. Now the 149 rule didn't fully cut it. We only ended up stopping just at our x-axis. So what I did was I extended it by adding the 16 on there as well. So it's a 149-16 rule. When I did the 16 part of the rule, 16 times -1 is -16. So going from up from 9 all the way down 16 points got me down at -7. But that's in the territory we're not allowed to go. So I flipped it up to +7 instead. Now what I'll do, because it is a graph that needs to be sketched, as carefully as possible, try to connect these points using an even flow. I like drawing what's actually staying the same first. So I will try my best to get these points. It's pretty hard doing this on a computer, but you're going to get the idea. And then of course, at the x-intercept, it's going to pivot upwards. And so I'll do it something like this. And this. Not perfect, but given that I'm doing it on a computer, it's not too bad. So we've sketched our graph. The question also wants us to state our domain and range. Domain, of course, is your possible x values. And really, if you look at this, you could throw in whatever x you wanted to. It's not like you're going to divide by 0 at any point. So we can actually say for our domain, we can say x is an element of all the real numbers. As for our range, however, range is all of our possible y values. Well, we can see by the ends of this quadratic that's been flipped up, this is going to go up to positive infinity. But the graph is not allowed to go below 0. So you can say this in a couple ways. If you like using interval notation, you can say it's going to go from 0 to positive infinity and use a round bracket on positive infinity because it's never actually going to get there. Or if you prefer another way, you could just say y is greater than or equal to 0. Either of those work. They both convey the exact same message, and I'm all right with both. Now, last up, this question wants us to make a piecewise function. Remember, the piecewise function is actually going to take our function and say what's staying the same and what's being flipped. What we can see, and I'll just do it in a different color so it sticks out, we can see that this section right in the middle here, the upside down little section up here, that's going to be staying the same. That's the exact same as if there weren't any absolute value bars. But this section onwards and this section backwards is actually flipped. So we're going to have to be pretty careful about how we express this in a piecewise function. What I would do, just to save some space, instead of writing out the whole absolute value function, I'll just say f of x equals our piecewise function bracket. We'll say the exact same function, negative x squared plus 2x, that's a squared, plus 2x plus 8, when x is between negative 2 and positive 4, because that's that stretch right here in the middle where that graph stayed the same. So again, x needs to be between negative 2 and positive 4, so I'll say negative 2 is less than or equal to x, which is less than or equal to 4. Okay, so x is a bigger number than negative 2, but x is a smaller number than positive 4. Now, the other part of this graph is flipped over. And remember, to flip over a graph, you just times the entire thing by negative 1. So the easy way to do that is just to say negative bracket negative x squared plus 2x plus 8. If you prefer to bring that negative through, you could write that as positive x squared minus 2x minus 8, whatever floats your boat. I honestly don't really care. Either way you write it, it's going to be when x is less than negative 2, so x would be less than negative 2, or x is greater than positive 4. Now you need to actually include both of these in here with your piecewise function, because again, it is flipped when x is less than negative 2 or when x is greater than positive 4. So you need to include both of those cases in your piecewise function. And that's it. So for practice, I want you to work on page 375 and do questions 1, 2, 5, and then 6, questions A, C, and E, question 7, and then question 8, questions A, C, and E. Now, I'm going to stress, you really need to do these. This has been a bit of a more challenging day than what we've been used to. Practice is absolutely essential in this. Now, a lot of these questions have to do with graphs. If you don't have graphing paper, I actually have some at the side of the room over by the formula sheets. Right? So if you check out the formula sheet wall, there should be some graphing paper waiting for you over there.